In pursuit of technical knowledge and just to gear up for the new engineering entrant, myself, Pranab Sinha Chaudhary, is here to deliver today's presentation, Power Transformer Part 10. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with differences between power transformer and distribution transformer. Based on power system service application, transformers are classified as power transformers and distribution transformers. Before analyzing the efficiency of transformer, it is necessary to find out the basic difference between power transformer and distribution transformer. Significant features: power transformer and distribution transformer used for in generating station and transmission network of higher voltages, that is 400 kV, 220 kV, 110 kV, 66 kV, 33 kV, and are generally rated above 200 MVA. For distribution transformer, in lower voltage distribution networks subjected to end user connectivity of voltage grade 11 kV, 6.6 kV, 3.3 kV, 440 volt, 230 volt, and are generally rated less than 200 MVA. Voltage application: step up in generating stations and step down in substations. Distribution transformer only step down voltages for supplying power to domestic and industrial units. Size and installation: for power transformer, larger as compared to distribution transformer and much technical complicacy to install. Similar as compared to power transformer and smaller in size and easy to install. Operating sequence: for power transformer, operate only at load transmission period and mainly at about full load condition. Usually, very less load fluctuations taken place. For distribution transformer, operate during load and no load period. Load fluctuations are very high. Significant features: copper loss and iron loss. For power transformer, more or less it is operating all the time in fully loaded condition. Hence, both losses will take place all through. Higher will be the copper loss than iron loss. So it has to be designed by having copper losses minimum. For distribution transformer, as it is not loaded fully at all time, so iron losses takes place throughout its operating period and copper losses will take place based on load cycle. Hence, it has to be designed by having iron losses minimum. Specific weight equals to iron weight by copper weight. Specific weight is very less in case of power transformer. And for distribution transformer, specific weight is more. Efficiency: nearly 100% efficiency in case of power transformer. That is maximum efficiency at full load condition. For distribution transformer, as average loading is somehow about 75% of full load, so designing in such a way that maximum efficiency would have to occur at 75% full load. Significant features: insulation level. In case of power transformer, high insulation level is required. For distribution transformer, insulation level as per voltage rating. Core characteristics. To scale down the mass of the ferromagnetic material, transformer core is so designed that it can have to operate slightly above the knee point value of its BH curve. Location of maximum efficiency point has to be adjusted where iron loss and copper loss will match. So for the distribution transformer is concerned, it is based on the typical load cycle for which transformer has to supply its core have to be designed by intercepting peak load phenomenon and all day efficiency parameter. Again, I repeat, based on the typical load cycle for which transformer has to supply, its core would have to be designed by intercepting peak load phenomenon and all day efficiency parameter. Flux density. For power transformer, higher as compared to distribution transformer. Distribution transformer, lower as compared to power transformer. Leakage reactance. For power transformer, it is designed with comparatively high value of leakage reactance. In case of distribution transformer, it is designed with low value of leakage reactance. Significant features: voltage regulation. Power transformer is not so much important regarding voltage regulation. But in case of distribution transformer, better voltage regulation is needed. Efficiency to be determined in case of power transformer by the ratio of output power to input power. In case of distribution transformer, better to use as the variation of load as exhibited throughout the day. So efficiency would have to be determined through calculation of all day efficiency. All day efficiency equals to output in kilowatt hour divided by input in kilowatt hour in 24 hours. Commercial efficiency. Most of the power transformers are supplying full load or nearly full load all the time, and their efficiency is determined by the ordinary or commercial efficiency based on the instantaneous power as supplied. That is, commercial efficiency in case of power transformer, output power divided by input power, that is output power divided by output power plus losses. Power transformers will have the higher copper loss than the coal loss. Iron loss or coal loss has a direct response with supply voltage only, whereas copper loss is related with the load current. Again, I repeat, iron loss or coal loss has a direct response with supply voltage only, whereas copper loss is related with the load current. Hence, coal loss stands constant whenever transformer primary is energized with rated voltage, but copper loss occurs only when transformer secondary is connected with load and becomes variable with change of load current. To have a better energy efficiency, power transformers should have to be designed with minimum full load copper loss. All day efficiency. In case of distribution transformers, whose performance cannot be judged by commercial efficiency as because of all the time, that is 24 hours in a day, usual load pattern is different from power transformers. Though the primaries of the distribution transformers are energized with the prescribed voltage all the time throughout the day, but there is a massive variation in magnitude of the connected load in secondary sites during the period of operation at off-peak and peak hours of the day. The load variation might have been from less than 30% of full load during off-peak period to cater full load during peak period of the day. Again, I repeat, the load variation might have been from less than 30% of full load during off-peak period to cater full load during peak period of the day. Hence, iron loss occurs in a continuous basis during the whole day, but copper loss occurs only when the load is connected with transformer secondary and would have to depend upon the magnitude of load. As due to have massive variation of load, the copper loss varies considerably during the day. Therefore, in a day, there will also be a massive variation in the commercial efficiency of such transformers while in operation. So, the performance of distribution transformers can have to be judged only by tracking their all-day operational efficiency. All-day efficiency would then be estimated only on the basis of usable energy for a specific time during the 24 hours, that is one day. In that case, load cycle should be of much importance to find out the all-day efficiency of a distribution transformer. Copper losses are variable losses as the load varies throughout the day. Copper losses are variable losses as the load varies throughout the day. Since the primary of distribution transformer is continuously energized, so the coal loss will also have to take place continuously. This is the reason for which a distribution transformer is designed to have a very low value of coal loss. All day efficiency equals to output power over 24 hours, that is input power over 24 hours, equals to output power over 24 hours divided by output power plus losses over 24 hours. Quantitative analysis of transformer efficiency. The performance of a transformer mainly depends on its efficiency and voltage regulation. As the transformer is being highly efficient in the range of 96 to 99%, and the losses are of the order of only 1 to 4%. Hence, the transformer efficiency is not necessary to determine with high precision by direct measurement of output and input power. Irrespective of power factor, the transformer losses are essentially be constant at full load current. But the transformer power output depends upon the power factor of the load. Whenever the load power factor drops, the output power will also drop for a given kVA rating, and simultaneously, the efficiency of the transformer also decreases. Now see the diagram, that is percentage full load current and efficiency, power factor, unity power factor, 0.8 power factor, 0.6 power factor. This is the maximum efficiency point. at unity power factor, and at this load current, copper loss equals to iron loss. The efficiency varies as with respect to two independent quantities. A, magnitude of the load current, and B, load power factor. Therefore, efficiency equals to output by input, that is input minus losses divided by input, that is 1 minus losses divided by input. Losses equals to copper loss plus iron loss. Now, copper loss I1 square R1, input power V1 I1 cos phi 1, efficiency equals to 1 minus losses divided by input, that is 1 minus copper loss plus iron loss divided by V1 I1 cos phi 1 equals to 1 minus I1 square R1 plus Wi, that is iron loss, divided by V1 I1 cos phi 1. Efficiency equals to 1 minus I1 R1 divided by V1 cos phi 1 plus Wi V1 I1 cos phi 1. That is equation 1. Now, differentiate the equation 1 with respect to I1. You see the result. That is dN by di1 equals to 0 minus R1 V1 cos phi 1 plus Wi V1 I1 square cos phi 1. Therefore, efficiency will be maximum when dN by di1 equals to 0. So, R1 divided by V1 cos phi 1 equals to Wi by V1 I1 square cos phi 1, then I1 square R1 divided by V1 I1 square cos phi 1 equals to Wi V1 I1 square cos phi 1. That is I1 square R1 equals to Wi. Therefore, it can be concluded that transformer efficiency will be maximum when copper loss equals to iron loss, that is variable loss is equal to constant loss. Why copper loss is a variable loss? Why it is called copper loss is a variable loss? Transformer losses which practically occur in loaded condition are the copper losses, which include I square R loss in the current carrying parts. Number 2 point, transformer copper loss is proportional to the resistance of the winding and square of the current flowing through the winding. Number 3, as the current depends on the load connected to the transformer, so the copper loss varies with variation in load. Number 4, when the load is increased, then the copper loss has to be increased because of the increased current and corresponding increase of resistance caused by the rise of temperature. This is the reason to conclude that copper loss is a variable loss. Why iron loss is a constant loss? Transformer losses will, while occur at no load condition, are the iron losses, which are the sum of the hysteresis and eddy current losses. Transformer iron loss is the implication of the power dissipated in the magnetic core subjected to a time varying magnetizing force. Iron loss has to depend upon supply frequency, maximum flux density of the ferromagnetic core, volume of the core, etc. So, hysteresis loss and eddy current loss both are dependent on the magnetic properties of the material used as the construction. And design phase of the core of the transformer. Hysteresis losses are proportional to the electrical frequency, and the eddy current losses are proportional to the square of the electrical frequency. As the above criteria of a former transformer typically remains constant, hence, irrespective of load current, the value of the iron loss is always be constant and continuous during whole of the lifetime the transformer is connected to the supply. Iron losses, therefore, are constant and be independent of the value of the load current. Now see the diagram, that is transformer efficiency versus load curve. You see the coal loss and copper loss efficiency, the maximum efficiency point. From the curve, it shows that the maximum efficiency of the transformer occurs while copper loss equals to iron loss. And the efficiency is maximum when transformer is operating near rated load. Note, efficiency is found to be low. Efficiency is found to be low while the transformer is lightly loaded, as because on this condition, both the hysteresis losses due to magnetization and demagnetization of the transformer core and eddy current losses are be in higher side as compared to output power. Again, I repeat, efficiency is found to be low while the transformer is lightly loaded, as because on this condition, both the hysteresis losses due to magnetization and demagnetization of the transformer core and eddy current losses are being higher side as compared to output power. When the load is further increased, then simultaneously efficiency of the transformer increases. If somehow transformer load exceeds the rated output value, then the copper loss has become higher as compared to output power, which results low in frequency. Transformer efficiency is defined as the ratio of its output power to input power and depends on both the load power factor and load current. Now, efficiency is maximum when iron loss equals to copper loss. Evolution of transformer core. In 1831, British physicist Michael Faraday, through the process of experimentation with Joseph Henry, had established the law of induction. Faraday's law of induction would have become one of the four Maxwell equations that define electromagnetic theory. With those background, historical phase of power transformer engineering has started its journey in the year 1886, when George Washington House, a pioneer of the electrical industry, had put his technological endeavor to build the first long distance alternating current for electric lighting system in Great Barrington, Massachusetts. George Westinghouse, October 6, 1846 to March 12, 1914, a resourceful, talented American entrepreneur and engineer based in Pennsylvania, had then to be apprehended that electric power could only be delivered over distances by transmitting at a higher voltage and then reducing the voltage at the location of the load. John Dixon Gibbs, 1834 to 1912, was a British engineer and financier who, together with Lucian Goulard, 16 July 1850, 26 November 1888 of France, had the credit to invent the AC step-down transformer. It was rather a first major breakthrough to build an iron transformer core which could act as a magnetic circuit. In 1881, their achievement was demonstrated and first exhibited as a device in London, of which electrical energy was made to transfer from one circuit to another through the use of inductively coupled conductors. The low voltage DC systems was being marketed by Thomas Edison's electric utility, which had a limited range due to the low voltage used. Westinghouse had, in a business sense, regarding the potential of alternating current to achieve greater economies of scale as way to build a truly competitive system instead of simply building another barely competitive DC lighting system using patents just different enough to get around the Edison patents, Thomas Edison's patents. Having with technological vision, American company Westinghouse had hurriedly gone for obtaining the US patent rights to the transformer developed by Goulard and Gibbs. In 1885, William Stanley Jr., his period is November 28, 1858 to May 14, 1916, an eminent American physicist, built the first practical alternating current transformer based on Goulard and Gibbs' idea. In December 1885, under a new contract with George Washington House, Stanley moved his operations to Great Barrington, Massachusetts. On March 20, 1886, having with technical and financial assistance of Westinghouse Electric and Manufacturing Company, William Stanley Jr. had successfully installed and demonstrated the first complete composite electrical network of multiple voltage AC power lighting system in Great Barrington, Massachusetts, for which 500 volt and 12 ampere AC power as delivered by a Siemens make alternating current hydroelectric generator for transmitting power to a distance of 4,000 feet, and then through transformers step down to 100 volts for supplying power over wide areas of illuminate incandescent bulbs in homes and businesses. William Stanley Jr., during his career, he was granted 129 patents for a range of products and electrical devices. Working for Westinghouse, the transformer core as built by William Stanley Jr. would definitely be judged a major breakthrough in the evolution of making transformer core. In the previous phase, the Gowlard-Gibbs transformer had seemed to be used a coil or many tons of iron wire to create a ferromagnetic loop, whereas in Stanley's model, transformer core was being used flat sheets of iron stacked together and clamped with wooden blocks and steel bolts. In no time, Westinghouse had taken initiative for commercial production, and the company's first commercial transformer had been shipped to Buffalo, New York, where a local utility placed it in service. Within months, the company also earned prestigious order for supplying another 25 numbers of alternating current plants. See the picture? Gowlard and Gibbs transformer and William Stanley's Harley transformer. In 1890, Stanley had launched his own establishment, naming the Stanley Electric Manufacturing Company in Pittsfield, Massachusetts. However, Stanley's transformer design concept became a prototype for future transformers, and his technical approach for AC distribution system was also become well accepted to form a logical basis of modern electrical power distribution. In around 1932, silicon steel sheet was readily introduced in the production of transformer core, as because silicon steel itself has the property of a good magnetic substance with strong magnetic permeability. In 1933, implementing the process of grain orientation also might have been a major breakthrough in the performance of electrical steels using as core materials. Since then, several effective steps, mainly in steel chemistry and the insulating properties of its surface coatings, are continued to be taken to expedite core process technology more user-friendly and cost-effective. Grain-oriented electrical steel, as processed under carefully controlled conditions to develop optimum magnetic characteristics in the rolling direction, would have to allow compact code designs requiring the minimum amount of material to be used in the windings surrounding the core. Through experience, it has also been exhibited If the thickness of the silicon steel sheet is thinner in size, then that is of size 0.18 millimeter to 0.5 millimeter. Then it has to contribute low losses. Again, I repeat, through experience, it has also been exhibited if the thickness of the silicon steel sheet is thinner in size, that is 0.18 millimeter to 0.5 millimeter, then it has to contribute low losses, not only in the core, that is no load losses, but also has to provide for minimum load losses or winding losses in the transformer. Basically, eddy currents mainly depend on two factors: A, thickness of the laminated sheets, and the frequency of the time varying current. So, thinner sheets are always be preferred for core construction. But reducing thickness of sheets, that must have to be degrade the stacking factor, which has also to affect the ultimate aspect of transformer core design. Stacking factor, another important point. What is stacking factor? Stacking factor equals to effective cross-sectional area of the transformer core divided by physical cross-sectional area of the transformer core. The formation of transformer core is usually comprised of thin metal sheets stacked in layers. To reduce eddy currents in the core while keeping a high magnetic flux, the laminations are individually insulated with some insulating material, which obviously of non-ferromagnetic characteristics. It is therefore the insulating part has to contain rather very negligible portion of the total magnetic flux. So, effective cross-sectional area of core equals to physical cross-sectional area of core minus area covered by non-magnetic insulator. Most of the magnetic flux is confined only within metal part of the core. That is sheet, within the sheet, metal sheet. During estimation of the magnetic flux density within the core, then the designers have to consider the stacking factor, which always be less than unity in case of laminated core. For solid core or non-laminated core whose stacking factor is therefore be unity. However, the stacking factor of laminated transformer core of silicon steel is of the order of 0.96. Silicon steel is a tailor-made iron alloy having specific magnetic properties of comparatively lesser hysteresis area, resulting in low power loss per cycle, low core loss, and high permeability. Again, I repeat, silicon steel is a tailor-made iron alloy having specific magnetic properties of comparatively lesser hysteresis area, resulting in low power loss per cycle, low core loss, and high permeability. Commercial silicon steel usually have the silicon content up to a limit of 3.2% is preferred for manufacturing cold rolled strips less than 2 millimeter thick. These strips are then cut to shape in size to make laminations which are stacked together to form the laminated cores. Higher concentrations of silicon content, more than 3.2%, would have been implied a change in basic metallurgical configuration of brittleness during cold rolling. That is the reason it should not be exceed, silicon should not, content should not be exceed 3.2%. Let's stop here. Further to be continued at later stage. Thank you. Thank you for patient hearing and listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments, feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.